Hello and welcome. This video presents our recent work on pose estimation refinement with ICP. In this work we investigate different design choices for ICP and propose a novel method that optimizes them based on an image of an object and the current ICP estimate. Let's begin by remembering how ICP works. ICP is an iterative algorithm for registering 2 point clouds given an initial estimate of their relative pose. ICP algorithms have two main design choices that largely influence their performance. The first is the choice of the data association method and the second is the choice of the error metric. A single iteration of ICP begins by transforming all model points to the frame of reference of the camera. A data association method then finds correspondences between the 2 point clouds. All correspondences are used to minimize an error metric. The output is used to update the current ICP estimate before it moves to the next iteration. The two most used data association methods are nearest neighbor and projective data association. To associate a single model point, nearest neighbor data association computes the distance between that point and every other point, and associates it with its closest neighbor. Projective data association stores the two input point clouds in vertex maps. Each pixel of a vertex map stores the 3D point that was projected to that same pixel in the image used to create it. Projective data association associates each point by projecting it onto the image plane of the second vertex map. The point stored at the pixel to which the original point is projected is then associated with it. We propose dynamic switching to optimize the choice of the data association method. This simple method first renders the object at the current ICP estimate. It then calculates a proxy for the percentage of points for which projective data association would fail to find a correspondence for. It then chooses projective data association if this proxy is lower than some threshold. Otherwise, it chooses nearest neighbor data association as is more robust to initialization. The two most used error metrics are the point-to-point error metric that computes distances between correspondences and the point-to-plane error metric that computes distances between points and linear surface approximations. We propose Cascading ICP to combine the strengths of these error metrics and minimize their limitations. Cascading ICP sequentially minimizes the point-to-point and then the point-to-plane error metric. Doing so reduces the probability of point-to-plane ICP diverging while benefiting from its potential superior accuracy. We now introduce the full hybrid ICP that combines dynamic switching, cascading ICP and point-to-point ICP. Hybrid ICP is an iterative algorithm that encapsulates the generic ICP algorithm. During each iteration, dynamic switching is used to optimize the choice of the data association method. If projective data association is chosen, hybrid ICP aligns the two input point clouds with cascading ICP. Otherwise, it aligns the 2 point clouds with point-to-point ICP. We consider the 20 shown objects in our simulation experiments. We use the top 10 objects to tune the hyperparameter used by dynamic switching and use the remaining 10 objects for evaluation. We benchmark hybrid ICP against other ICP variants in 3 different experiments. The first investigates hybrid ICP's robustness to initialization noise, the second to noise in depth images, and the last to noise in object models. We have found that hybrid ICP is significantly more robust than the baselines. The left column of the following 2 slides illustrates ICP initialization. The remaining 3 columns compare the output of hybrid ICP to that of other baselines. As shown, hybrid ICP is the most accurate. We also consider the setting in which ICP re-estimates the pose of an object as the camera moves into it. The video embedded in this slide illustrates such a scenario. In both videos, green represents the ground truth pose and red the estimated pose. In this setting, we investigate the trade-off between each estimate's accuracy and computation time.